Welcome, everyone. I'm Dan Powers, the Executive Director of the Society for Science at User Research Facility, and I want to welcome you to the session this afternoon, the end of our first day during the 2022 annual meeting. It's going to be with Dr. Zachary Hood. And Zach is giving a user research project update, a bit of a spotlight, and the title of his research is Solid-State Electrolytes for Lithium Metal Batteries, Bridging Nanoscale Phenomena and Their Macroscopic Performance. So I'm going to let him describe that in any more detail. I won't try to add a little more context, but let me give you a little background on Zach. He's been a great participant, helped us in last year's annual meeting, and someone I got to meet actually in person as those kind of gatherings are happening again. I know he's been recognized for his work by the Materials Research Society, and that was the conference where we got a chance to meet just last week. Let me describe a little more of his background. He's a scientist, a materials scientist with the Applied Materials Division of the U.S. Department of Energy's Argonne National Laboratory, and he works on emergent electrochemical materials. He develops innovative synthetic materials to produce new solid-state materials and leverages a number of characterization techniques to understand their properties and performance from the nano-to-macro scale. I also know from some of his previous years of research and his work after he graduated from Wake Forest, I'd just been doing my research on the presenter, Zach, and I'd like to bring up how, in addition to this level of deep physics and science and chemistry that he's involved in, he also had spent a year after graduating from Wake Forest building schools and children's homes in Honduras, and he still is involved in that kind of philanthropic work with a U.S.-Pakistan startup initiative and is involved in Boston's Partners in Education. So I just appreciate that broader spectrum of interests and the sort of things that he has as part of his life. And I want to mention that as something we should all aspire to, having that amount of sort of vision in how you want to spend your time in addition to the deep science that you're involved in. Thanks, Zach. So Zach, over to you.
Yeah, thank you so much, Dan, for the kind introduction. So my name is Zachary Hood. I'm a materials scientist in the Applied Materials Division at Argonne National Laboratory. I joined Argonne about 3 years ago, and I now lead a small team focused on advanced electrochemical materials for next generation applications, including batteries, electrocatalysts, and conversion processes, and among many other different applications. I'm also the incoming chair of the User Executive Committee at Oak Ridge National Laboratory Center for Nanophase Material Sciences, where I've served since 2017 as the secretary and the vice chair. I actually got involved with the user's facilities whenever I was a student many years ago, back in 2014. And the user facilities have really been a great asset for my career, not just as an intern and as a student or as a postdoc, but now as a scientist. And today I really want to highlight some of the work that we've completed over the last several years through a number of different user projects at a few of the different user facilities. So the title of my seminar today is Solid-State Electrolytes for Lithium Metal Batteries, Bridging Nanoscale Phenomena and Their Macroscopic Performance. And in today's seminar, I'd like to highlight solid-state electrolyte work that has been largely completed over the last 5 years, and specifically highlight aspects of this work that was enabled by scientific user facilities. Much of the work presented today was completed at Oak Ridge National Laboratory Center for Nanophase Material Sciences, as well as Argonne's Center for Nanoscale Materials. In today's talk, I plan to focus on solid-state electrolytes and their application in next-generation lithium metal batteries, and I will also reflect on some of the previous lessons that we've learned on a number of classes of these solid-state electrolytes, and highlight the new and electrifying opportunities that these materials may offer. So in line with the goals of today's talk, I have separated this presentation into two parts, which are exemplified by the following guiding questions. I will start by addressing the questions, can we reimagine the next generation battery? And what's the hype around the solid state electrolytes? And then next, I will delve into two guiding questions. Number one, what can we reveal at the nanoscale for next generation batteries? And how have scientific user facilities enabled an enhanced understanding of these next generation batteries? If I do my job today, you should be able to leave this talk and answer these questions in light of what has been shared. So to begin, let's quickly discuss lithium-ion batteries. So a lithium-ion battery has three indispensable components. It has your anode, which is generally a carbon-based material that theoretically allows for one lithium ion to be stored per 6 atoms of carbon. Second, you have your cathode, which is generally a lithium transition metal oxide, such as lithium cobalt oxide, that allows for intercalation of the lithium ions into the layers. And lastly, you have a liquid-based electrolyte, which is generally a lithium salt dissolved in an organic solvent. Although this technology has become central to our lives in the form of portable electronics, it must be improved for applications that would allow society to radically change its synergy with renewable energies sources such as solar cells, windmills, tidal electrifiers, and so on. I mean, as such, let's take a look at some of the chemistry and engineering challenges associated with these liquid-based lithium-ion batteries that incorporate liquid-based electrolytes. First, there are some instabilities at the electrode-electrolyte interfaces, and generally lithium-ion batteries have a lower temperature window that prohibits their use in colder or warmer climates. And then lastly, we need to consider the damage resistance and the safety of this technology. Replacing these flammable liquid organic electrolytes can not only make these batteries safer, but also it could enable a new range of materials that could be integrated as the anode or the cathode for these next generation batteries. On the right-hand side of the slide, I show an ideal high-energy battery stack, which is composed of a composite cathode, a lithium metal anode, and a solid-state electrolyte between the two. The solid-state electrolyte is envisioned to enable energy-dense anodes and cathodes that will allow for batteries with higher specific energies. But note that this idealized battery structure requires a solid-state electrolyte with a thickness of around 20 microns or less. So let's take a quicker look into this solid-state battery stack. So if we consider the length scales and form factors of different cell components, we can estimate the cost distribution for these batteries. When considering the solid-state electrolyte, this component is likely to contribute to around 1/3 of the total materials cost. However, these cost estimates are based off of using solid-state electrolytes with using 20 micron thick solid-state electrolytes, which are around 1/4 the diameter of your hair. But in terms of these cost estimates, it really motivates my work because they are quite significant for these next generation batteries, and we must consider this moving forward. So when considering this dimension of 20 microns or thinner, methods to produce our solid-state electrolytes generally yield materials that are either too thick or too thin. Going thick makes your battery have more volume, meaning that you can store less energy per unit volume. And if your electrolyte is too thin, your battery may not hold a charge and it could potentially fail. So there's a sweet spot, again, between 1 and 20 microns in thickness that we really need to target and urgently, for the United States to have competitiveness in the space of manufacturing. So in terms of these batteries and solid-state electrolytes, there's still very much to learn about different battery constructs and solid-state electrolytes. And this is especially in the realm of the work that guides my personal research now at Argonne National Laboratory. In the field of solid-state ion conductors, I work on the design and synthesis of solid-state electrolytes. Next, my team implements these new materials into actual devices and evaluates their performance using a number of electrochemical methods, such as cell cycling, electrochemical impedance spectroscopy, and so on. And lastly, I use unique methods to interrogate interfacial electrochemistry at the nanoscale to better understand these devices. And some of these methods will be highlighted in today's talk. Of course, We need to understand these materials in order to replace the liquid-based electrolytes in traditional lithium-ion cells. And some of the most prevailing examples of solid-state electrolytes that will be highlighted in today's talk are oxynitride-based materials, oxide-based solid-state electrolytes, and sulfide-based solid-state electrolytes, which will, of course, form the basis of today's seminar. So at this point, we must ask ourselves, how can these solid-state electrolytes be integrated into next-generation batteries? And how have scientific user facilities enabled and enhanced understanding of next-generation batteries? Here, I'd like to use some of my previous work to highlight key examples of what we were able to learn from different classes of solid-state electrolytes, specifically at the Department of Energy's Nanoscale scientific research centers. So in my first example, I'd like to introduce the concept of interface formation between lithium metal anodes and solid-state electrolytes by highlighting some of our recent work that our team completed on the solid-state electrolyte lithium phosphorus oxynitride, known as LiPon. Although LiPon has a relatively low ionic conductivity, LiPon-based microbatteries have been shown to cycle over 10,000 times with lithium metal anodes. And the lithium metal anodes are generally less than around a micron in thickness when they start. However, there's much to really be learned about this interface between the lithium metal anode and the solid-state electrolyte for us to better improve materials for these next generation batteries. And so to interrogate this interface between the lithium metal anode and LiPon, we developed a novel method to look at the interface by touching lithium metal and the LiPon solid-state electrolyte in situ at the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. Here, we applied transmission electron microscopy using a unique piezo-controlled holder that allows us to directly touch the materials and apply an electrochemical bias across this interface. So on the left-hand side of the slide, you can see the general experimental setup that was designed at Oak Ridge National Lab. Here, we deposited LiPon directly onto a polished copper grid and lithium metal onto a tungsten tip. After carefully transferring these materials into our electron microscope, we then set off to interrogate exactly what happens at this interface. On the right-hand side of the slide is a video of actually what happens in situ. So I'll play that now. So this is the interface that forms between LiPon and lithium metal. So as you can see, upon touching the lithium metal and the LiPon solid-state electrolyte, there is an outward growth of LiPon towards the lithium metal anode, signifying a volume expansion of LiPon and the formation of what we call and refer to as the interface. So looking further into this interface formation, we can calculate the area expansion ratio of the interface as a function of time. As shown on the left-hand side of the slide is a plot of the area expansion ratio as the function of time with three distinct regions. Region 1 is the onset of this reaction. Region 2 highlights where the reaction is kinetically limited. And region 3 is the stable region, where no further growth of the interface was observed, even after an external bias of 5 volts. To further interrogate this interface, we applied electron energy loss spectroscopy, known as EELS, to better understand the chemistry and the electronic structure of the interface formation. So using EELS, a material is essentially exposed to a beam of electrons with a known narrow range of kinetic energies. And some of the electrons will undergo inelastic scattering, which means that they lose energy and have their paths slightly and randomly deflected by the material. The amount of energy loss can then be measured via an electron spectrometer and interpreted in terms of what caused that energy loss. So we looked at specifically the lithium, the phosphorus, oxygen, and nitrogen regions of the material and saw some clear differences between the pristine solid-state electrolyte LiPon in comparison to the interface. So dramatic changes were observed in the lithium K-edge in the EELS spectra for the interfacial layer. Instead of multiple peaks observed in the lithium K-edge for the pristine LiPon, there were 2 main peaks in the lithium K-edge for that interfacial or interphase layer, implying that the lithium bonding configuration is significantly altered within the interface. It is also interestingly noted that the nearest neighbors of the lithium and light bond are primarily oxygen and nitrogen based on previously reported theoretical calculations and neutron scattering. So our microscopy results, including both these in situ imaging as well as our electron energy loss spectroscopy analysis, provided two important points regarding the stability of our solid-state electrolyte light bond with the lithium metal anode, which is schematically shown at the bottom hand of this slide. First, when light bond is contacted with lithium metal, an interface forms as a result of light bond decomposition and at the very surface of that light bond. Second, the thickness of the interface is limited to around 50 nanometers and does not grow with time, even after an external bias of 5 volts, which means that this interface layer is effectively stabilizing light bond with lithium metal and may contribute to the long life of light bond being used in next generation all solid state lithium metal batteries. So information provided in this work fills the knowledge gap regarding the electrochemical stability window of light bond and its high stability and cyclability in all solid state batteries. Furthermore, this interface contains a high concentration of phases with high lithium ionic conductivity, such as lithium nitride, lithium phosphide, and several other phases, which may explain the good interfacial conductance of the light bond lithium interface. So now that we know that light bond, of course, reacts with lithium metal to form stable interfaces, we wanted to understand what happens with solid-state electrolytes that have an overall higher lithium ion conductivity, such as lithium garnets. Using the same technique, we interrogated the interface between lithium metal anode and the classic oxide-based solid-state electrolyte lithium garnet material. We have especially in our groups of making both crystalline and amorphous lithium garnets, and as such, we were able to interrogate both types of structures. So, seen in this video on the right, we can touch the lithium garnet with lithium metal anode, and we can further jam the lithium metal into the electrolyte. So, as we touch the metallic lithium to that amorphous lithium garnet, in comparison to the lithium phosphorus oxynitride materials, we do not see or observe a significant change of that interface. In fact, if there is any change at this interface, it is significantly smaller than what we observed with light bond. The EELS data on the lower left-hand side of this slide schematically shows what happens on the electronic structure. And EELS line scan across this interface shows very tiny difference in the oxygen K edge of this inner layer, being confined to around 5 unit cells. And this change is correlated to a phase transition of the interface, which stabilizes that interface. So using these types of techniques, we really can reveal the stability of lithium metal with solid state electrolytes, as well as the morphological changes in our materials. So moving along, we must also ask ourselves, how can these solid-state electrolytes be integrated into the next generation batteries? And based on some of our previous lessons learned from light bond and these lithium garnets, I plan to focus on some of the most recent examples of actually manufacturing these solid-state electrolytes by highlighting some of our recent work with lithium garnet films and how these materials can be processed in a new way to create films for next generation batteries. So to address the need for scalable processing techniques to manufacture thin solid-state electrolytes, we invented and applied a new spray process technique that allows us to manufacture solid-state electrolytes as films that are both thin and slim. The concept is quite simple. We can dissolve our precursors directly into a solvent, spray the solution onto a heated substrate, and grow films of our materials. By adapting not just the deposition temperature, but also the post-processing temperatures, we can make films that have either a polyamorphous type of structure, or we can get fully crystalline films of our materials by adapting some of the processing steps that we integrate into how we fabricate these solid-state electrolytes. But importantly, this method has allowed us to start to grow films that have thicknesses between 1 and 20 microns, high density and are pinhole free. And this is what we envision to enable the manufacturing of some of these next generation solid-state batteries. So we further investigated the dynamic processes during the film formation using differential scanning calorimetry. Here I want to highlight a few of the main processes. With differential scanning calorimetry, we can measure the heat flow as a function of temperature. Here we can see a few specific endothermic and exothermic events. Remember, we can first deposit our film onto a heated substrate, and then depending on what type of crystallinity we desire in these films, we can then heat it and crystallize our films up. At 250 degrees Celsius, we can see that some of our constituents can melt. We can have some of our constituents decompose. And then lastly, we can get crystallization of these materials. So in one example with the lithium garnets, we were actually able to observe some of the melting processes that actually happen using the in situ capabilities of the Center for Nanophase Material Sciences. So this is a video that shows that first process of when we deposit our materials and then undergo the melting of the materials. We can observe all these events that happen at the nanoscale. But importantly, with the crystallization of these materials, we can take our films and then take it to the temperature where we would want to crystallize our material to get a dense solid-state electrolyte. And we can observe the nanoscale transformation of these films. So as you can see in this video, we can see that the film has amorphous grain boundaries and larger crystalline grains. And as the material is heated, we can see these nanocrystallites start forming at these grain boundaries, which then get consumed by the larger grains. So then the larger grains continue to grow inward, and eventually they form a triple junction. By applying these unique microscopy capabilities at the Nanoscale Science Research Centers, we can not only understand the interface of solid-state batteries, but now we can also understand the fundamentals of the synthesis and processing science that surrounds how we make films of these solid-state electrolytes. So speaking of which, we also recently revisited the fundamental synthesis and processing science of sulfide-based solid-state electrolytes that I prepared while I was an intern and student at the Center for Nanophase Material Sciences. Within sulfide-based solid-state electrolyte system, we were interested in exploring solid electrolytes that utilize low-cost materials such as sulfur and phosphorus. Classically, solid-state methods were explored to synthesize lithium thiophosphates using evacuated Pyrex or quartz ampules. And this results in the gamma phase of these lithium thiophosphate-based solid-state electrolytes. And at Oak Ridge National Lab, we demonstrated that we can synthesize lithium thiophosphates using innovative solution-based processing techniques using polar solvents, such as acetonitrile and tetrahydrofuran. While the reaction is relatively straightforward, we are generally left with co-crystallized solvent in the material that must be removed with heat and vacuum. And by doing so, we are left with the beta phase of the lithium thiophosphate with the PNMA space group. And if we take a look at the measured ionic conductivity of the bulk lithium thiophosphates versus solution processed lithium thiophosphates, we can see a significant difference in some of their properties, such as lithium ion conductivity. The bulk gamma phase of lithium thiophosphate has a room temperature ionic conductivity on the order of 10 to the minus 7 Siemens per centimeter, whereas solution processed lithium thiophosphates have room temperature ionic conductivities on the order of 10 to the minus 4 Siemens per centimeter, an improvement about 3 orders of magnitude. But what is the root cause of this improved lithium ion conductivity? Or more clearly, can we interrogate these materials at the nanoscale to better understand their structure property relationships? So to get a deeper understanding of this material, we have developed and leveraged capabilities at the Center for Nanoscale Materials at Argonne National Laboratory in order to characterize films of the sulfide-based solid-state electrolytes. Traditionally, sulfides are electron beam sensitive, and at Argonne Center for Nanoscale Materials, we leverage the unique Argonne chromatic aberration-corrected transmission microscope known as ACAT. This microscope enables a low beam dose rate and the capability to reveal the amorphous and crystalline structures in lithium thiophosphates at the atomic scale, as shown on the right-hand side of this slide. This characterization allowed our team to better understand the phase transformation of these materials and the impact of crystalline size on the observed macroscopic ionic conductivity, or how fast the lithium ions can move through the crystalline and amorphous regions in the lattice. This result also reveals the importance of grain boundary chemistry on the macroscopic performance of solid-state electrolytes. And so, as mentioned in this previous example, grain boundary chemistry is particularly important for solid-state electrolytes. But for many examples of these materials, little is actually known regarding the exact chemistry and electronic structure of the grain boundaries. When considering the oxide-based solid-state electrolytes, again, the lithium garnets that I mentioned earlier, grain boundaries are present when we make these materials and sinter them into a dense ceramic. However, the influence of these grain boundaries on the macroscopic electrochemical performance were largely overlooked in the literature. So to interrogate this point of the influence of the grain boundary chemistry, we leveraged advanced scanning transmission electron microscopy and valence band electron energy loss spectroscopy in order to reveal the local atomic and electronic structure difference at the grain bulk and at the grain boundary of lithium garnets. Specifically, we use this unique capability to show the band gap of the grain bulk and how it compares to that grain boundary. At the grain bulk, we measured the band gap in the material to be around 5.7 to 5.9 EVs, so it's mostly insulating and compares well with other measurements for what's theoretically predicted of this material. However, at the grain boundary, valence band electron energy loss spectroscopy revealed that the band gap was drastically reduced to around 1 to 2 EVs, which is reminiscent of a semiconductor. And this is not what we want necessarily in a solid-state battery. So this difference in the band gap can cause a flow of electrons into the grain boundaries, and it can potentially even cause the nucleation and propagation of lithium filaments within our solid-state electrolytes. These lithium filaments are known to short circuit a battery, which can then cause battery failure. So to look a little bit closer at these lithium filaments can be seen using scanning electron microscopy images after symmetric cell testing at increased current densities, which is shown on the top right-hand side of the slide. But in polycrystalline LLZO, the filamentary structures are largely confined to these grain boundaries. So the results that we collected at Oak Ridge National Lab really highlight the importance of these grain boundary chemistries and their electronic structure. It also paves the way to some new research that really guides what we're doing for future solid-state electrolytes. They would highlight the importance of tuning not only the grain boundary chemistry and the electronic structure for these next generation ion conductors, but also the interface between the lithium metal anodes and these solid-state electrolytes. If a lithium conducting and electron insulating phase can be interposed between lithium metal anodes and the solid-state electrolyte, it may positively impact the current density that one could achieve in a full lithium metal battery. So in conclusion, I'd like to revisit why we are interested in solid-state electrolytes. In today's talk, we discussed some of the main challenges associated with energy storage, as well as how solid-state electrolytes could enable next-generation high-energy solid-state batteries. While these materials have a number of tantalizing properties, studies that link their nanoscale phenomena with their macroscopic performance have paved the way to an enhanced understanding of these materials. And this understanding is expected to pave the way to next-generation high-energy solid-state batteries in the coming years. So at this point, I'd like to acknowledge my colleagues, collaborators, and team who contributed to this research. I've worked with a number of excellent colleagues across many institutions, Argonne, MIT, Oak Ridge National Laboratory, Samsung, and others. I've had the privilege to mentor a number of Sully students and research aides and postdoctoral appointees over the last few years who have contributed to this work. I'd also like to acknowledge funding from Argonne National Lab, as well as user facility support who supported this work largely. Specifically, I'd like to acknowledge Oak Ridge National Laboratory Center for Nanophase Material Sciences, as well as Argonne's Center for Nanoscale Materials. At this point, I'd like to take any questions from the audience, and I really thank you for having me and for the invitation.
Okay. Thank you very much, Zach. That is some fascinating detail. It seems like it's moving quickly. If I could characterize it that way, what you were referencing and the pace by which it seems you're discovering particular nuances is kind of wonderful. I'd like to think where this could lead to a next generation of, or even it seems like a bit of a newer paradigm of battery technology is part of what we need to enable our whole new energy paradigm we're looking to move forward to. Let me check here on our questions, and I know we're up to time as well. No, I actually just had a statement of thanks coming in from somebody on the details there. So let me ask, this might be a little off to the side, but in terms of some of the process, you had mentioned creating some new spraying solutions to be sure that you got the film just to the kind of thickness that you wanted. It made me think of existing 3D printing technology, and I wondered, is that one particular facet particularly difficult, or is that actually, did it just catch my brain and it's really, that's not a big deal, that's not something to notice?
No, yeah. So spraying, controlling our spray solution chemistry, we put a lot of effort into engineering the actual chemistry that we have in these spray solutions, but we envision them to potentially even be put into some maybe 3D type of spray processes where you can have structural batteries in a way, right? So we do at Argonne, we do have spray printers and, ways that we can spray with, very specific form factors. Of course, it's not, the form factors you can get aren't down to that nanoscale, but, we're at the length scales that are relevant for at least lithium metal batteries. Yeah, and so these techniques that we're really pushing for in terms of the spray processing, we've had to invent kind of new types of spray solutions, new types of paradigms in the synthesis and processing science to enable us to really get to these thicknesses that you can't achieve for classic ceramic processing. Yeah, and we put a lot of intention into how we design these spray solutions, and then also leveraging ways at the user facilities for us to understand how these materials evolve, after we deposit them and post-process them, to have the structure and chemistry and a number of other aspects that contribute to their electrochemical properties.
Great, thank you. All right, I like getting just some more of that story there to what you're working on. Well, thank you again for making time and having such a intriguing presentation. And that's going to be the end of our sessions for this very first day. Thanks very much, Zach.
Yeah, thank you guys so much for having me.
Yes, and before we go, I would like to bring up just one slide. And for those who are still on the call, just a brief prompt on the schedule for tomorrow. For the people who were able to stay till the end, just a reminder of the topics that will be coming up tomorrow. We get into a mix of communications, of legislation, and the realms of congressional forces that can impact the activities within user facilities and federal research laboratories. And then back into a somewhat of a deeper dive into some nanotechnologies relative to microelectronics that Adam Rondinone will be speaking about at the end of the afternoon tomorrow. So that will do it for our sessions of the first day. I look forward to seeing many of you tomorrow. And please tell others, this is open to everyone. And we'll be recording these and sharing them as well so they can be watched on demand when it's convenient. I'm Dan Powers, Executive Director of the Society for Science at User Research Facilities. Thanks for making some time for us today. I'll see you tomorrow.